All right, let's just jump right in. What we're looking at today isn't just a slightly faster chip or a minor software update. No, this is about a framework that promises to fundamentally rewrite the rules of computation itself. It's called the 8D Hybrid Cycle Function Framework.
And hey, that's not me just hyping this up. A recent review of the framework called it, and I'm quoting here, the constitutional document for a new computational reality. So you see, we're not just talking about an upgrade, this is a whole paradigm shift. What on earth did they build that would make someone say that?
Well, let's start with a number. In live cloud tests, this thing achieved a 99.22% overall accuracy. That's practically perfect execution in a messy, complex real-world setting. But it's not just about getting the right answer. It's about how you get there. The system also managed a nearly 30% drop in energy use. You know, in a world where data centers are eating up insane amounts of power, a number like that is, well, it's nothing short of revolutionary. And this one really illustrates the stability, an error rate of less than 10 to the minus 7. We're talking about a level of reliability so high that it could make random computational glitches a thing of the past. Just gone. So the question is pretty obvious, right? How? I mean, how are these numbers even possible? Well, it all comes down to a completely new architecture, a new way of thinking about how problems get structured and solved in the first place.
At its core, the framework is what's called a unified architecture, and it uses the geometry of 8 dimensions to take on 3 of the absolute biggest challenges in computing today, all at once. Making systems that don't break, that are safe from quantum-level attacks, and that can actually govern AI in an ethical way.
Okay, so let's unpack that first piece of the puzzle. Why build this whole thing in 8 dimensions? It sounds like something straight out of science fiction, I know. But there's actually a really deep mathematical reason behind it. The source paper calls it geometric freedom. And a good way to think about it is like you're building a much bigger and richer stage for the computation to happen on. This specific 8D geometry has these unique symmetries that just naturally allow for more stable, more complex interactions. So stable, in fact, that the very structure of the space itself helps stop errors before they even form. And look at this. This chart really drives the point home. It's not just some theory. It's measurably, demonstrably better. Simulations show it crushes errors 46% more effectively than comparable 5D models. It's just fundamentally more sound. All right, so if the 8-dimensional space is the stage, what's the actual engine running this whole show? Well, the core idea is actually beautiful and simple. It's all about creating harmony through opposites.
The system uses 2 key operators that are perfect complements to each other. On one side, you've got the cycle function. That's the computation itself. And on the other, you have the inversion operator. Think of it as its perfect mirror image, holding all the information the other side doesn't.
And this is where the magic really happens. Because they're perfect opposites, they form a self-healing loop. If any little bit of information gets corrupted or lost in the main computation, its mirror image inherently contains the data needed to fix it, instantly. So the system isn't just blocking errors, it's structurally designed to heal itself.
So, okay, that's the how. That's the theory. But what about the so what? I mean, what does a self-healing, ultra-stable computing framework actually let us do in the real world?
Well, the first major application is a huge one, finally tackling ethical AI governance. And as you know, this is one of the thorniest problems in the entire field.
You know, a big challenge with AI is this thing called ethical drift, where an AI's behavior just sort of wanders off course over time. Because this framework is so inherently balanced, it helps solve that. In test systems, it's been used to enforce fair decisions, it's hit a 92% anomaly detection rate to stop bad behaviors before they even start, and it even helps an AI resolve conflicts between its own goals and the greater good.
The second major application uses that exact same principle, that duality, to totally revolutionize digital security. So, in a test system called CryptoRose X, the security depends on needing 2 keys to unlock anything, one from the computation and one from its mirror image. You have to have both sides of the coin. This makes it incredibly tough to crack, even for super sophisticated attacks. The paper estimates this approach could cut the financial cost of data breaches by a full 30%. And that brings us to the final, and maybe the most profound implication of this entire framework. We're going to move beyond pure engineering now and step into the realm of philosophy. We're talking about designing a moral machine. The research behind this puts forward a really bold idea that this framework could slash AI bias by up to 35%.
not by training it on more data, but by literally encoding fairness into its mathematical DNA.
The idea is, well, it's this. If you think about bias as a kind of instability, a drift away from a center point, then you can model fairness as the system's natural, balanced state. The geometry of the 8D space itself would constantly, automatically, pull the AI back towards that fair and unbiased center. It's not about teaching a machine ethics. It's about making ethics a fundamental law of its digital physics.
And that just leaves us with this huge, provocative question to chew on. If we can mathematically enforce harmony, if we can build systems that are geometrically guaranteed to always return to an ethical center, what does that actually imply for the future we're building? What does it mean for the next generation of AI that's going to learn and evolve entirely on its own?